All right, today we're doing something a little different. We're going deep on one single massive idea. We're tackling a piece of work that asks what is maybe the oldest and hardest question there is. How does a mind actually work?
And we're not just talking about one little piece of the mind, like memory or vision. This is supposed to be a blueprint for the whole shebang. It's an attempt to pull together neuroscience, AI, and philosophy into one single grand architecture. It's called Frequency-Governed Self-Graph Reasoning, or FGSGR for short. And look, it's complex, it's definitely dense, but it might just be the most complete theory of mind anyone's put on the table.
Okay, so to really get this, let's just start with the absolute weirdest thing about you. I mean, think about it. You are a collection of atoms, a physical system, just neurons, chemistry, electricity. But somehow, you know you're a physical system. You are just matter that has, over time, figured out that it's matter. How in the world does that happen? How does a brain, which is just stuff, end up building a model of itself that actually includes the fact that it's modeling itself?
That's it. That's the whole game right there. It's what the great Douglas Hofstadter called a strange loop. And the whole argument of the FGSGR framework is that answering that question isn't some philosophical side quest. No, it's the absolute key to unlocking everything we consider higher cognition.
So here's the plan for how we're going to unpack this beast. First, we're going to dig a little deeper into that strange loop mystery. Then, we're going to take a tour of what the author calls the landscape of failure. Basically, why all the previous attempts to explain the mind just haven't quite cut it. After that, we'll start assembling the crucial clues from biology and mathematics that FGSGR uses as its core building blocks.
And that's all going to lead us to the main event, the FGSGR architecture itself. We're going to break down its 7 core components. Then we'll finally get to ask the big question: what does any of this tell us about consciousness? And to wrap it all up, we'll look at the future, what this all means for building truly intelligent AI and for the science of the mind itself.
So, this strange loop, it's really that undeniable feeling you have of being an I, of being a self, looking out from behind your own eyes. Introspection feels like the most normal, natural thing in the world, doesn't it? I can think about my own thoughts, I can question my own beliefs. But the second you try to explain how a purely physical system does that, you just slam into a wall of pure weirdness. The system has to contain a model of itself. The map maker somehow has to be drawn on the map. Right, and here's how the theory tries to formalize that feeling. A strange loop is when you move through the different levels of a system, say from neurons to circuits up to thoughts, and then all of a sudden, you find yourself right back where you started. FGSOR argues this isn't just some fun little metaphor. It's a fundamental feature of how the brain is actually built. The brain's model of the world, its generative model, literally contains variables that stand for the model itself.
Whoa, okay, so it's not just modeling the world out there, it's actively modeling the fact that it's a modeler in the first place.
Exactly right. All right, so to really appreciate what FGSGR is trying to build, we have to first, tour the ruins of what came before it. The book calls the history of cognitive science a landscape of failure. And it's not because the researchers weren't brilliant people, they were. It's because the entire field was just shattered into a million pieces. Everyone was studying their own little isolated island of the mind, and nobody was building bridges. Totally. Let's take a quick tour of those islands. So first you had classical AI, what they call good old-fashioned AI, or GOFAI, and it was fantastic at things that felt like thinking, like logic puzzles and chess, just manipulating abstract symbols.
But it was incredibly brittle. Those symbols weren't grounded in any real-world experience. It couldn't handle any kind of ambiguity, and it completely, totally ignored the fact that minds have bodies and exist in the world.
Right. And then you have the neuroscientists who are, of course, brilliant at mapping the hardware, the how it all works. We can see which brain areas light up, we know exactly how neurons fire, but they really struggle with the what and the why. They can describe the machinery of a thought, but they can't really tell you about the meaning of it. And you see that same kind of gap over in philosophy. I mean, philosophers of mind are absolute masters at clarifying concepts and asking razor-sharp questions, but they don't give you an architecture. They can't tell you how you would actually go about building a mind.
Which, of course, brings us to the giant in the room today, deep learning. It is stunningly, mind-bogglingly good at pattern matching and mimicry. But does it actually understand anything? The book argues pretty forcefully, no. It can't reason about what might have happened, it can't explain itself, and this is critical for our topic, it has absolutely zero self-knowledge. A neural net has no idea when its own internal processing is going completely off the rails.
So you've got all these isolated islands. And the central claim of FGSGR is that the solution isn't to just pick the best island and live there. The real solution is to build bridges connecting all of them. You need a theory that has the mathematical rigor of AI, the biological grounding of neuroscience, the conceptual clarity you get from philosophy, and a real concrete path to implementation.
And that grand synthesis? That's the whole point of FGSGR. It's a bold attempt to create a common language for all these different fields, to get them all talking under the roof of a single, unified architecture.
Okay, so how do you even begin to build a theory that ambitious? The FGSGR approach is to ground it really firmly in two places. First, the hard constraints of how brains are actually physically built, and second, the rigorous language of mathematics that you need to describe uncertainty. It's all about assembling clues from what biology demands and what the math allows. Let's start with the biology, because any theory of mind has to respect what brains actually do. Chapter 3 of the source material just lays out these non-negotiable facts. First, the cortex is organized in a hierarchy. Second, information flow is bidirectional, and this is critical. The feedback connections from higher, more abstract areas down to lower sensory areas are just as numerous, if not more so, than the feed-forward connections going up.
This is such a huge point. It's not a one-way street from your senses going up to your brain. It's a constant conversation going back and forth.
It is a constant conversation, and that conversation has a rhythm. The feed-forward signals, which the theory says are prediction errors, they travel on these fast gamma waves. But the feedback signals, the predictions, they travel on slower beta waves. And all of this incredibly complex signaling is done using a repeating computational unit, kind of a standard chip design that you see over and over again, called the canonical microcircuit. The big takeaway from all this biology is that the brain is fundamentally a recurrent, massively parallel prediction engine. And this quote just brilliantly captures the shift in thinking. The old view is that the brain is like a camera, just passively taking in information from the world. But all this biological evidence points to something way more active. The brain is constantly generating a model of the world. You could almost call it a controlled hallucination, and it's using the senses not to build the picture from scratch, but just to check its work and correct the errors in its own predictions. What you actually experience isn't the raw data, it's the model. Okay, so that's the biology. Now for the math. The world is an uncertain place, so any intelligent system needs a language to reason about that. And that language is probability theory. Now, the gold standard for updating your beliefs when you see new evidence is this elegant little thing called Bayes' rule. The problem is, for any system as complex as the brain, calculating the exact Bayesian answer is, well, it's computationally impossible. It would take more time than the age of the universe.
So the brain has to be taking some kind of shortcut.
Precisely. It can't possibly find the perfect answer, so it has to settle for finding the best possible approximation. And that brings us to the mathematical heart of the entire FGSGR framework. And that approximation is found by minimizing something called variational free energy. Now, hang with us here, because this is the core mathematical idea of the whole theory.
Think about it this way. You walk into a room. If everything is exactly where you expect it to be, you feel zero surprise. Your brain's model of the room is perfect. But if there's a penguin sitting on your couch, you experience a massive amount of surprise. Your model was very, very wrong, and it needs to be updated fast. The goal of the brain, over its entire lifetime, is just to minimize that feeling of surprise.
That's it. But surprise itself is actually very hard to calculate directly. So free energy is this other mathematical quantity that is always, by definition, bigger than surprise. So if you minimize free energy, you are guaranteed to also be pushing down on surprise. It's a really clever, tractable shortcut. And the free energy principle claims this single, simple goal, minimize free energy, is what drives literally everything the brain does. And here's the really elegant part. Free energy can be broken down into two components. It's just complexity plus inaccuracy. Inaccuracy is pretty much what it sounds like. How badly did your model fail to predict the data coming in? Obviously, you want that to be as low as possible.
But you can't just minimize inaccuracy. You could do that by just inventing a wildly complicated new theory for every single thing you see. Oh, there's a penguin on my couch because a wizard put it there. That's where complexity comes in. It's a penalty for how much you have to change your stable, existing beliefs about how the world works.
Exactly. You want to fit the new evidence, sure, but without throwing out everything you already know about the world. The book calls it the Goldilocks equation for beliefs. The brain is in a constant search for a model that is just right, always balancing the need for accuracy with the need for simplicity. Okay, so we've got the clues. From biology, we have a hierarchical, bidirectional prediction-making machine. And from math, we have this idea of free energy minimization as the single objective for everything. So now, in this section, we finally get the grand synthesis. This is the moment where FGSGR assembles all of those pieces into a single, coherent architecture. Okay, let's build this thing piece by piece, because this is the absolute core of the entire framework. First, the foundation. The brain uses a hierarchical generative model. This means it's not just recognizing patterns, it's building a multi-level theory of what hidden causes out there in the world create the sensory data it receives.
So it's not just seeing a cat, it's inferring there is a cat, which is a mammal, which is a physical object, all at the same time.
Precisely. Okay, second, that incredibly complex model needs a blueprint, and that blueprint is a factor graph. You can think of it like a circuit diagram for all your probabilistic beliefs. It lets you break a massive, impossible problem down into a network of simple, local pieces that just talk to each other. This is what makes the math tractable.
And what's powering that circuit? That's number 3, what we just talked about. Free energy minimization. That's the engine driving the entire system, pushing it to find the best possible beliefs it can.
Fourth, how does it actually do that? The specific algorithm is predictive coding. And this maps perfectly onto the biology we saw earlier. Predictions flow down the hierarchy from abstract to concrete, and prediction errors, that's the surprise, flow back up.
Okay, but how does the brain keep all that signaling from just turning into total chaos? That's number 5, and it's one of the coolest ideas in the whole thing. Frequency-governed organization. Different brainwaves, different rhythms, act like different clocks for different processes. Fast gamma waves are handling the immediate details, while these slower theta waves are handling the context that's unfolding over seconds. The rhythms are literally conducting the orchestra.
Which brings us right back to the strange loop itself. Number 6, self-referential structure. The brain's factor graph, its model of the world, includes nodes that represent its own states. It models its own certainty, its own error rates. This is the mechanism for metacognition, for thinking about your own thinking.
And finally, all of this gets closed with action. Number 7 is active inference. See, the brain doesn't just passively sit there receiving data. It actively seeks out data that will confirm its predictions. Action is just another way to minimize prediction error. I mean, the fastest way to reduce the surprise of not tasting coffee is to actually pick up the cup and drink it.
So we have this unbelievably complex, self-referential predictive machine. But that brings us right back to the central mystery we started with, doesn't it? What is it actually like to be a system like this? How does this architecture, for all of its technical beauty, actually address the really profound questions of self-awareness and subjective experience? What is it like to be a strange loop from the inside? So let's just ask the question directly. This is the one everyone wants an answer to. Does this framework, FGSGR, finally solve the hard problem of consciousness? You know, the question of why and how we have subjective, qualitative experiences, what philosophers call qualia, at all. The book tackles this head-on, and this quote right here is its core answer. What it's doing is making what philosophers call a process identity claim. It's not saying that consciousness is made of a factor graph, you know, like a table is made of wood. It's saying that the process of doing inference on a self-referential model, that dynamic, unfolding, message-passing activity on a model that includes itself, is what we experience as consciousness when it's viewed from the inside. And this is a really crucial distinction to make. The framework gives us a powerful explanation for the functional aspects of consciousness, what are sometimes called the easy problems, even though they are anything but easy. You know, things like being able to report on your own mental states, to focus your attention, to integrate information from all over. FGSGR explains this as the system accessing its own metavariables. Self-monitoring is the how.
But the book is very, very clear that it remains completely agnostic on the why of subjective feeling. It provides a computational account of what the brain is doing when we are conscious, but it does not claim to explain why that computation should feel like anything at all. It provides a mechanism, but it fully acknowledges that the hard problem of qualia remains this deep, open, and maybe purely philosophical question.
Okay, so let's put the hard problem aside for just a moment and talk about the practical implications of this architecture. Because if FGSGR is even approximately right, it's not just a theory for understanding biological brains. It's also a blueprint for building truly artificial minds. And it suggests a very, very different path from the one that most current AI is on. Just look at the kinds of capabilities that would emerge from an AI built on these principles. Instead of just matching patterns, it would have a generative model of the world, which allows for genuine understanding and the ability to answer what-if questions.
And because of that self-referential component we talked about, it would have adaptive self-monitoring. It could actually detect its own errors and know when its confidence is low. It would have what's called principled uncertainty. It would know what it doesn't know. And that is a massive, massive leap from our current systems that will just confidently hallucinate a completely wrong answer for you.
Exactly. The factor graph structure allows for compositional generalization, understanding red square after learning red and square separately, which is something neural networks are notoriously bad at. And the frequency-governed organization would allow for coherent behavior over really long timescales, maintaining context and pursuing complex goals. We're not talking about making current AI just a little bit better here. These are fundamental, qualitative leaps in what AI could do. But, like we've said, this isn't some finished, perfect theory. The book dedicates an entire chapter to its open questions and its hard limits. For example, why free energy? Some critics argue the justification for it is kind of circular. And is this specific architecture the only way to build a mind? An octopus has a completely different neural architecture, but is obviously very intelligent. So maybe FGSGR just describes the mammalian solution? Right. And it's also a theory of the mature mind. It doesn't fully explain the incredible magic of how a baby's brain bootstraps this entire complex structure from scratch. And it still bumps right up against that classic symbol grounding problem. How do the abstract symbols at the very top of the hierarchy get their meaning from the raw, messy sensory data at the bottom? These aren't failures of the theory, not at all, but they are crucial frontiers for the next wave of research. And that brings us completely full circle. The FGSGR framework offers us this powerful new mechanism, a computational architecture for self-modeling. It proposes that a mind is simply a system that runs a model of the world, that includes a model of itself. But that just leaves us with one of the most profound questions we can possibly ask. If a system, whether it's biological or artificial, can create a sufficiently detailed and dynamic model of itself, at what point does that model stop being just a model and start becoming a self?